How does one actually develop a powerful, efficient, and future-proof hydrogen plant? And what role does the right technology stack play in this? That's what I'm talking about today with Nikolaj Szeliga. He is a technology expert in our conversation, deeply involved in process engineering, down to the smallest detail, and can also step in as a process consultant. And Philipp is joining us again, who always gives us the overall perspective on what we need when we want to enter the hydrogen business sector.
Get ready for Hydrogen, a Siemens podcast with Michael Pretorius and Philipp Glaser.
You'll have to help me out. I need to grasp this technology stack. It sounds pretty complex. What exactly are we talking about here, Nico? What all comes together technically?
The technology stack is ultimately a representation of our Siemens portfolio for hydrogen. That means it consists of many different components that we've put together for our customers, planners, builders, and operators of hydrogen plants to help them plan and operate their facilities faster, better, and more efficiently. And it's made up of various templates for our software tools, planning documents, and blueprints, cybersecurity, plant safety, and other needs at a hydrogen facility, measurement technology, careful selection, automation concepts, and so on.
From what I've seen with you so far, Philipp, it's really a whole collection, a whole range of different components that can be combined with each other. Can these things also be used individually? Do I always have to think in terms of the entire portfolio? Does it not make sense otherwise?
Well, that's a very important point. You can use the whole thing, but you can also just use parts of it. That's really important. On the one hand, of course, that's our basic motivation. The motivation was that we looked at hydrogen plants and saw that although they have very individual uses, they also involve individual requirements. But when you look at the components of such green hydrogen plants, they are consistently similar. And so the idea was to say this could be used for standardization, for standardized engineering. And of course, we've reflected that in all of our tools. So for example, in the area of plant engineering with COMOS, for simulations in GPROMs, for example, for automation in PCS7 or in SIMATIC PCS Neo. Basically, everything is included, but I don't have to use everything. Of course, it's also intended as an enabler to implement a fully integrated digital hydrogen plant.
We've already talked about this in the other episodes, how helpful the digital twin is when it comes to planning the plant. You just mentioned the software COMOS, and for simulation, you brought up GPROMs as the software solution. You also just mentioned your process control system software PCS7 or PCS Neo. Nico, you're deeply involved in the topic of engineering for process technology. Maybe you can give me 2 or 3 examples of what such blueprints and engineering templates specifically look like for hydrogen in your case.
Yes, of course. One example is that we took a look at the hydrogen plant, how it is engineered, what it looks like, which process units it includes, and for each of the main components, we created 1 or more templates, which we also planned out from an engineering perspective up to a certain stage. I'd say up to the end of basic engineering, not fully detailed down to the last element, but to a solid planning level. So that in the engineering phase, especially in the initial and very early stages, rapid progress can be made. We have meticulously developed these templates in our advanced engineering software COMOS as detailed flow diagrams, along with the equipment and instrumentation lists. We built a similar library in GPROMs, or have them built by our colleagues in the simulation team, and now a customer can take these. They are relatively generic, but thanks to the excellent work of our colleagues, they still offer a high level of accuracy.
Let's get more specific, perhaps with specific examples. I'll ask the question again. Nico, can you maybe, if you could, give me a few examples of how you work with these templates? In detail, please, for us, in your experience, and elaborate on this topic. After all, hydrogen plants can look very different in the end. There are some that differ regionally, based on their topographical conditions. There are some that are built for different sizes. To what extent have you already taken this into account in the planning software COMOS, so that I know exactly where my electrolyzer is located? how it is connected to the other plant components, and what components I need on site. Give me examples of this technology stack. What does it look like? What preparations have you made?
For the technology stack, we actually, in terms of our approach, carefully designed and meticulously engineered a plant. We specifically chose a reference size that had already been built by our colleagues in Germany, around 10 megawatts, and re-engineered it using our planning tools. For example, we created flow diagrams, equipment lists, and instrumentation layouts using our engineering planning software. Together with our simulation colleagues, we then reproduced these in GPROMs using a generic approach. Subsequently, since we can't include customer-specific data in our software without their consent, and then make it available to clients. Nevertheless, we achieve high accuracy in the simulations thanks to the physics-based algorithms in GPROMs. Using ready-made templates, customers and our engineering colleagues can now quickly set up detailed plant designs and easily simulate them across various scenarios to explore potential outcomes. This is especially helpful in the early phases where feasibility is being assessed, feasibility studies, initial design considerations, and of course, as the process continues, further simulations can be run with additional information. This way, the plant, the digital twin, can also be developed in parallel with the engineering process.
In one of the previous episodes, we talked about business models and financial planning. Also, for such a plant, there are many components that come into play. Whether such a plant can ultimately be operated profitably, if I now have to adjust certain factors to fit these templates. How easy is it then to tweak the parameters, to individualize things for my specific plant?
So the important thing first is to be able to say, how can I quickly get to the point where I have a plant concept? And everything that is already prepared that I can use generally makes me much, much faster in that phase. To give an example, if you want to make an investment decision now, whether you can build a hydrogen plant at a certain location, that naturally, obviously, of course, is dependent on many factors. What kind of electricity do you get? Where do you get it from? At what price do you get it? What about the water supply? How much water do I need? What is the plant's capacity? How do I transport it away? So there are a lot of framework conditions that need to be decided and defined. Now, of course, I could start calculating things somehow in Excel and piecing things together. Then, in case of doubt, I might also have to convince some investors with it. But if I can already set up a generic initial simulation here, then I immediately have a completely different foundation, which I can, of course, refine further during the engineering process. But the important thing is it's not all empty to begin with. I'm not starting from scratch with a blank sheet of paper. And accordingly, the tools that have now been mentioned are not empty either, but already contain something, namely a generic hydrogen plant, to the extent that it makes sense to prepare it generically.
Earlier, Nico, you mentioned all these various process engineering approaches. How important is it, in your view, to be familiar with hydrogen when preparing and planning such processes? Or are these components truly interchangeable across different industries?
Okay, good. It's important to be familiar with the process. We see this time and again when customers come to us. We have a very split picture here. On one hand, there are customers and hydrogen stakeholders coming from the field of renewable energy, meaning photovoltaic systems and wind farms, operators, planners, developers. And on the other hand, we have many companies from the traditional oil and gas or process industries. And the questions that concern these customers are fundamentally different. The oil and gas customers have been working with hydrogen for over 100 years. You don't need to explain the process technology to them. For them, it's more about needing support with the rapid planning of the plants, with the digitalization of the facilities, so they can produce their hydrogen as efficiently and cost-effectively as possible. This also involves questions such as the product carbon footprint. In other words, how many CO2 equivalents am I producing per kilogram of hydrogen produced? Since they are mostly still producing gray or blue hydrogen, these are important issues. So, the digital hydrogen plant, and they are usually planning on a larger scale, meaning hundreds of megawatts that they want to install gradually, even reaching into the gigawatt range. We see startups from the Power-to-X sector, which often come from academic environments or from renewable energy developers. They often underestimate what it means to operate a hydrogen plant, because they usually, though not always, have little knowledge of process engineering and also of the safety concerns that come with such a process engineering facility. Hydrogen is a highly explosive and flammable gas. It is volatile. Consider safety and explosion protection. They often overlook this unknowingly. They think, we'll just set up a few electrolyzers, like we put up a few wind turbines, and that's it. Not the case. Control systems like SCADA, PLC for small plants, or DCS for large facilities are needed. We need plant safety, we need safety concepts. We absolutely need a safety-oriented circuit in this plant, within the automation system. We need monitoring, we need trained plant personnel, who, in most cases, are also present on site, and many other aspects that are standard in the process industry, but which are unknown to those outside the process or industrial sectors. And for them, or especially for them, this blueprint, this tech stack, is incredibly important. Even if their plants might look completely different, they might use different electrolyzers, different sizes, different downstream processes that we haven't represented or haven't yet represented. But still, the same planning conditions, the same general framework, of course, apply. And for them, of course, it's incredibly important that we provide them with something that shows them which steps they need to consider in planning, what core components such a plant has, what additional peripheral systems exist, and which input and output conditions they need to take into account. And of course, they do not just get this naturally dumped on their doorstep and are left to figure it out on their own. We also offer additional support in the form of consulting and engineering services to assist them, if they wish, as well. That is, of course, something my department also provides them as part of our comprehensive services.
Philipp, you mentioned it earlier, this large portfolio of services, technology, blueprints, templates. So, if I'm hearing you correctly, on the one hand, these are really, I'd almost call them plugins or some kind of templates that you can load into your existing software products to speed things up on the software side, right from the start. But these blueprints are also simply action guides, like checklists that I can review in advance in order to find the right answers to the most important questions together with my partners from the industry. Questions that might not have even occurred to me in the first place. And at the same time, you also offer services, meaning that you can essentially bring your expertise into a company during the planning phase. But I also gather, Philipp, that during the training phase, it's about familiarizing the personnel who will later operate the facility with all the safety precautions and the efficient operation of the plant.
Yes, absolutely. We can mention a few examples here. So we recently had a customer visit us again at the process automation world, and it was exactly the kind of customer Nico described, someone from the renewables sector. They had built and were operating around 20 solar parks, and now they want to expand their portfolio to include hydrogen plants of various sizes for different purposes. This is done partly to simply make use of excess capacity, which is available, but also to drive the decarbonization of larger plants, which is a significant goal. This ranged from 1 megawatt to 300 or 400 megawatt per facility, typical projects that they were considering to pursue. But even here, during the conversation, we quickly realized for many of the questions that would have been important to us to have a concrete conversation with them about what they actually need, how they envisioned it, how they would like to set up automation, how they plan to handle maintenance during operation, how they intend to ensure the long-term performance of the plant. You could tell there were more question marks than answers. And at that point, of course, that's where the real strength lies, that we not only have the technology stack, but also Nico and his colleagues, because we naturally involve them at that point. They can, in fact, guide the customer at that stage and are actually able to step in where you realize there's still a lack of maturity in the basic considerations. That's something that was also new for us or for me, because I was used to speaking with specialized departments in other processes where there were many highly competent people. Here it's partly different, and we can also take these individuals by the hand here and together with our dedicated support carefully and patiently bring them to the level of maturity that is needed in order to efficiently move into the engineering, construction, and operation of hydrogen plants.
Can both of you give me some insight on that? What kind of timeframes are we talking about here when we say that the plant planning uses your templates, these blueprints? How long does it take to build such a plant if one follows these templates?
The closer the plants our customers are planning align with our templates, the more direct value they gain from them, and the faster they can plan their facilities. Of course, it's always difficult to give fixed percentage values here, like use the templates and you'll save exactly 53.21%. I would never make such precise claims as it's not realistic, but of course, we can state that, depending on when the customer approaches us and makes use of these engineering templates, they can save valuable time and, accordingly, also money in the planning process. As a result, this can lead to even greater efficiency overall. And of course, that also depends on how much of these templates they actually use, how much of the tech stack they utilize. If they only use the automation part, which is typically planned out relatively late in the project, even though the automation concepts are, of course, developed in the early phases, then naturally, the added value and the time they save in engineering are limited. However, if they start early, maybe before deciding, and use the entire technology stack, then they can save 10 to 20% in every phase. Another added value is not just the time savings, but also the avoidance of planning errors, having a clear roadmap, and ultimately, when using planning tools, having various digital twins, whether for the plant itself, for maintenance and servicing, for an operator training system, or for plant optimization. And of course, if you build them from the very beginning, you can create them cost-effectively and continue to use them. That's obviously a major advantage during operation.
But I'm also picking up on the idea that the earlier I familiarize myself with these templates and blueprints, the more they help me make an investment decision, and possibly also convince partners in the market that I need to take the first steps. I imagine it a bit like looking at the assembly instructions for a shelf I haven't even bought yet. And then I say, maybe I'd prefer a different one, or actually this one is just right. Or maybe I need a bit more space in the living room. Or am I off track, Philipp?
No, that's exactly right. Basically, we try to talk to customers at a very early stage, ideally when they're still in the feed phase, that is the front-end engineering design phase, the fundamental concept phase, definitely before the final investment decision, to already get a sense of which direction things are heading. What's important for us in the initial conversations is to get a sense of what role we as a company could play in a project with a customer. And also, from a general philosophical standpoint, how does the customer actually plan for the plant to be built and operated? If I simplify it very broadly from our perspective, there are basically two different types. There's the type where we say, yes, the whole concept resonates. We're going for this digital hydrogen plant. We want to use all these concepts in operations. We also want to benefit during the engineering phase, making it faster and easier by using this technology stack as much as possible, and also to standardize. I'm already thinking about my second, third, fourth plant, how I can reuse this. Then for us, that's a customer where the entire story of the digital hydrogen plant resonates. And that's where we would fully engage with the whole concept, supporting this customer from an early stage. The other aspect is that there may be customers who say, well, I'll hand this over somewhere, maybe to an EPC, and they break it down into the typical packages and simply offer products and services according to a service catalog for each category. That's a very important point. With many plants, especially new companies, that's the case. In certain situations where individuals might not possess the complete background information themselves, these so-called EPCs or engineering, procurement, and construction contractors are frequently utilized. These are companies for engineering, procurement, and construction, which take on the actual implementation of the plant, turnkey or under whatever contract form, similar to a property developer. And this is a very important point. A common scenario in plant construction, everyone knows this from building a house with a property developer, is that there are naturally different interests involved. Of course, in the end, everyone shares the general interest that a plant or a house is built, that everyone agrees on it, and that it gets paid for. But when it comes to the details, a builder naturally has different interests than a property developer, and so on. And it's similar here. In the end, we have to take a close look. Take the EPC, for example, the one building the plant. They don't necessarily have a contract structure that also takes into account operation, maintenance, and similar aspects over the next 20 years. That means if a customer says, I would like to use the digital twin for all these topics like hydrogen performance, optimization, and so on, then of course a digital twin would be very useful. But in some cases, a certain portion of this engineering work isn't done by the customer themselves, but rather by service providers on their behalf. And now comes the important point. Now, of course, the point is that I have to tell this service provider, listen, I don't just want the house to be standing at the end. I also want to receive the engineering work, or at least the parts of the engineering that I need. Of course, not the entire engineering, because that includes elements that are part of their intellectual property. But I need this digital twin afterwards for the operation. And at this point, of course, we can help everyone involved. Why? Because on the one hand, we can help the customer sharpen their understanding of what exactly they need for this digital twin. We can also assist them by using our technology stack to define what requirements need to be set in order to actually obtain it. And thirdly, we can of course help the EPC by saying, look, it's already prepared. You can use that. That means if you choose to, and this is open, that's a very important point. We don't make anyone dependent on us. The components can be used, they can be further developed, they can be customized, and so on. You know, we've often talked about this open hybrid ecosystem that is our focus. In that sense, we're trying to bring together all the different parties involved in plant engineering to develop a shared interest through this technology stack. And that's how an optimal plant is created.
I can already tell. It totally makes sense to sit down with you in Karlsruhe sometime. You mentioned the process automation world earlier, the PAW, where you can actually see all of this in action. And you've also published a guide where you can already download the most important documents. And it definitely makes sense to tap into both of your brains, your know-how, and to meet with you and your colleagues in advance. To set the right steps in motion right from the start. Thank you. Great to have you with us.
This podcast was done by humans but localized with the help of AI. Thanks for listening.